All right, so we have two warm-up problems, right? First one's just an integral, just to practice it. And if you don't have the idea of how to do it yet, this is the perfect time to figure out that information. And number two is a callback to actually the previous chapter, like way, way back when we first started learning, some calculus stuff. Taking derivatives, you should be able to do these derivatives. Hopefully you still remember those rules for those derivatives. And yeah, just get those in there. And while you guys are working on that, wanted to point out a timeline of where we're at and how things are going. So if you can't see the problems, it is on the pair deck. So please go ahead and make sure you're open with the pair deck and start answering those questions on there. All right, so here's the deal. What I have planned so far is we're going to finish up this unit like today, probably. Yeah, most likely today. If not, like the beginning of next week, like Monday-wise. And we're going to start reviewing for your test. Your test is going to be after spring break. So I'm going to be giving you a study guide and your Delta Math study guide sometime next week. So then you can work on it sometime next week. And then if you don't feel like it, you can work on it through spring break if you want to. But you can do it. It should be doable so that you can finish it before spring break. That way you can enjoy your spring break. Okay, and then after spring break, you come back, we'll review on the Monday we come back, and then take the test on the following Tuesday. So when we come back from spring break, you will have a review with me, and then your test will be, we'll see how we do on that review. So your test is most likely going to be on this Tuesday on April 6th, but I might push it to April 8th to see where we're at. That's a little iffy though, because like I said, we have to push through a couple chapters here. So this is our unit 5, right? Which is technically unit 6. I break things down a little bit slower. So once we finish this, we only have about 2 more units to cover. One is the applications of integrals, and then the other one is the I think it's like the volume of it and other miscellaneous stuff, I believe. Let me double check real quick. Yeah, indefinite integrals and volume. Yeah, one of them is indefinite integrals, meaning integrals that go on forever. They don't have like 0 to 1. And then the last chapter is the volume stuff, which is applications of these integrals. So we only have like 2 more chapters left, and it's doable. It's doable, but it's really crunching down on our time. So like I said, this unit test should be on April 6th. We should be able to do the next unit covered and finished by April, hopefully a little bit before the end of April, and then the last unit hopefully before the second week of May. Your test is going to be on May 24th, the AP test, and I am expecting you to take it. Remember, if you take it, I curve your final grade very good, very, very, very well. Like your final will be, very, very curved. If you don't take it, then your final will not be curved. I will be grading it straightforward and straight up. If you take it and just get a 1, that's what you want to do. What time is it going to be at? The AP Calc exam is always at 8 a.m. Is always at 8 a.m. So you need to get there before 8, and then they'll place you in different classrooms. I think there's going to be like, I think they're going to separate you into like 3 different classrooms or so, because there's 40 of you, and they can only have like 15 or so in the classroom. So they'll make sure you're separated and you're socially distanced, so you don't have to worry about all that. But yeah, hopefully you'll be there. So that leads me to my second thing. How do we pay for the exam? That's a good question, Brian. I will go and ask that for you. I feel like your exams should be free though, right? It should be waived, I thought. If at most it's $5, right? Because you're all on reduced, you guys are all on free lunch programs. So I think it should be free, but if anything, the most you have to pay is $5. It shouldn't be more than $5. If it is, you guys gotta let me know, and then I'll go talk to the assistant principal for you. But that leads me to my next thing. It's been a while. It's not been a while. I don't actually know your schedules, but I know some of you guys have been struggling to, actually, I don't know that about you guys either. But I know that some students are struggling to focus by 8 a.m. because of this whole, learning from home type of deal. And some students have been waking up, logging on to the classes, and then kind of like not really there, but you guys still do the work afterwards. that's all well and good because you still do the work for my class. I'm perfectly okay with that. But it's going to be hard for you to shift gears if you're not used to thinking at 8 a.m. So what I'm going to do is incentivize you guys to start thinking and doing problems at 8 a.m. or before 8 a.m. actually, around 7:30-ish. And the way I'm going to incentivize this is to offer you extra credit. In the month of May, once we start wrapping up our units here, our last unit, and we start wrapping up and we start reviewing, in the month of May, what I'm going to be asking from you from Monday through Friday, so the 3rd through the 7th, the 10th through the 14th, and the 17th through the 21, these 15 days, I'm going to be offering problems from 7:30 to 8. Just one problem in the morning. You have to get up, get on before 8, solve this problem for me, and turn it in between the windows of 7:30 to 8. That shows me that you're awake at that time and you're able to think. They're not crazy, ridiculously hard problems. They're going to be like something you can do in like 5 minutes. But again, if it's not right, you'll still get the extra credit. If it is right, you'll get more extra credit. But this is the window for your extra credit right here. If you're struggling and you're worried about your grade, this is the easiest extra credit you can do. All you need to do is wake up, try your best on that problem, turn it in before 8, and do that for these 15 days, and those are the extra credit points that will definitely go towards your grade. And I'm talking major extra credit points. Like if you are getting a D in my class and you do this right here and you take my final and you fail my final, I'll pass you with a C. Like if you have a D, if you have a low D, I will boost it up to a C. If you have a B, I need to see what your final is. If you have a B and you fail your final, that's going to be hard for me to boost you to an A, but I won't drop you from a B. Does that make sense? Like I can't just push everyone up a letter grade. Percentages don't work that way. If you have a D and you fail the final, you're still going to be around a D. If you have a B and you fail the final, that drops your grade down to like a C. But with this extra credit incentive, I'm hoping to keep I'm basically trying to like push everyone to a C or higher, right? So I don't want you stressed out about your grade in here. I want you to just try your best at these problems. I want you to try your best on the AP exam, right? So don't worry about getting things wrong. Just try to focus on how to do the problem. Don't worry about the points. Don't worry about your final grade. I am trying to just make sure you understand, like, you shouldn't get a D in my class. I don't think you can get a D if you just, I think the only way you can get a D is if you just stop trying. I think that's the case I'm trying to make here. As long as you're trying and you're putting in the effort, you're turning in stuff, and the stuff you turn in isn't great, you're still trying. So don't stress out too much about it. But yes, that's the extra credit incentive I'm trying to have here for you from the 3rd to the 21st. I was going to do a poll, and I was going to ask you guys eventually, how would you guys feel about Saturday sessions or Sunday sessions for review? Also towards extra credit as well, but I need to find out if you guys would be down to meet up online on a Saturday or a Sunday to do problems together, and then not mornings. Well, actually, maybe mornings to get it done and out of the way, to get you used to doing things at 8 a.m. I'll send out a poll. I'm going to create a poll. I'm going to send it out, have you guys fill it out. Just be honest about it, and then we can figure out what times would be best for people and what days would be best for people. Maybe not weekends if you guys prefer, like after school. If you want to do it, like we could do like, in the evening times, 6 p.m. to 7 p.m. or something like that during the weekdays as well. I'll send out a poll and let you guys know, and we can go from there. Okay, so that's the gist of it. If you have any questions, let me know. Type into the chat. I can talk to you about it. But yeah, let's see how you guys did on this warm up while I was rambling on and on and on and on and on and on about this stuff. Let me go ahead and move this over here. How's everybody doing today? Hopefully you're doing okay. Yeah, it's not bad. You guys are mostly spread out around the middle here. One person is off the charts. Who's this one person who is off the charts? Are you legitimately off the charts stressed? Are you not? If you are, maybe you want to talk to me about it. If you're just being dramatic, then okay. We'll just leave it at that. I don't want to belittle your actual stress. So let me know if you actually are off the charts. If you need a break, or if you need something, me to do something to help you out with that for my class, let me know. There's nothing like, I'm not going to ask you this, and then when you tell me like, oh, I'm actually overstressed with your homework, I'm not going to come back and just be like, oh, well, that's a shame. Here's more homework. You know, that's not how that's going to work. So just let me know if there's something that I can do for you. All right. All right. Let's move on here to this slide. Without a calculator, find the integral from 0 to 1 of 4x cubed plus x squared plus x. Right. I'm going to star a couple answers here that I just want to share with you. Oh, I like this. I like this answer. It's not what I was asking for, but I like this answer. And one more. Let's star one more. So let's take a look at these answers here. I just want to show you what some of your classmates have been putting down. Right? So this is beautiful. This right here, right, is using the fundamental theorem of calculus. If I ask you to do the integral without a calculator, you need to find the antiderivative. Oh, don't worry about it, Leslie. I got you. I got you. Let me see here. Let me double check though, Leslie, that you are here. Leslie R. Yeah, I got you. I got you. Yeah, you made it. You made it. We're just doing these warm up problems. If you want to join in, it's this Pear Deck link right here. We're going over it, but you can still write on there if you want to do so. All right. So, like I said, right, the integral without a calculator, right, is just using the antiderivative. Okay, using the antiderivative. I'm gonna go ahead and scroll down to this next one. So I don't know if the evaluation part is right, but it looks right. You just plug in the 1 in here and minus it by plugging in the 0. And that looks good. That looks good. You can leave it as a fraction. You can write it as a decimal. Both are acceptable answers. I like this answer. This isn't what the question's asking for you to do, but I like this answer. I really do. This is converting an integral into the limit notation. This is the definition of an integral, right? And this is actually done very beautifully. 4 times delta x to the third plus delta x to the second plus delta x. That's what they're doing here by replacing those x's with that. And the delta x is equal to a plus k times 1 over n. So I didn't ask for this one, but this is beautifully done. This is beautifully done. But this is not the answer for this question. The answer for this question, right, is the other way. This, if I give you a problem in this form, you would need to be able to go back to the integral and then do it this way, right? Do it by taking the antiderivative. But I have to say though, kudos on converting it correctly into the limit form. That is awesome. Not many students are comfortable with this, but whoever this was, good job, good job. All right, and this is the one, the last one that's very similar to the first one, right? Again, the antiderivative is what's being used here, right? And how do you know it's the antiderivative? Well, if you look at this line right here, this student put down x to the 4th as the antiderivative of 4x cubed. All you have to do to check if something is the antiderivative is take the derivative of your answer, and if you end up back at where the problem starts, you have your antiderivative. What am I saying? What's the derivative of x to the 4th? The derivative of x to the 4th is 4, by the power rule, you bring down 4x to the 3rd, right? We would do 4 minus 1, right? So that's the correct antiderivative of this one. For x squared, it is x to the 3rd, right? But if you take the derivative of x to the 3rd, it would be 3x squared. There's no 3 there. And the way this student fixed that problem was by putting a 1/3 right there, And same thing with this x right here. The derivative of x squared would be 2x, which would be the right power. So to get rid of that 2, the student put a 1/2 in front to counteract that measure. So this 1/2 will cancel out with that power when you use the power rule to take the derivative. So this is the antiderivative. Now, the next thing I wanted to show was the difference between the first student and the second student right here is this line right here. You will not get marked wrong if you don't include that line, as long as you're showing that you're evaluating this function from 1 to 0, which the student did on the second line. If you don't show that though, you don't write anything else and you just stop here, you will lose out on points. This is called an evaluation line. It's evaluating this function at these points. It's going to be 1 minus 0. And it's just good practice to do, just to draw that evaluator line. Okay? So it's not mandatory, but it's just good practice to do. It is very good practice to do. Okay? So hopefully everyone is okay with that and understands that. So they plugged in here, and they didn't plug in the 0 right here because 0 to the 4th plus 0 is 0. Yeah, it's okay that you didn't write the minus 0 right there. That's perfectly fine. All right, and then you got here 11/6. That looks Beautiful. Good, good, good. So those are the answers right there. And I'm going to go ahead and, you know what? I'm just going to do this. I was going to write this all out, but why don't I just do this? I'm going to screenshot you and give you a forever place in my notes right here. So the answer for number 1 is this right here. Boom. There you go. That's the answer for number 1. All right, let's go to the second problem. Second problem is just asking you to tell me the derivatives. Tell me the derivatives of each of these problems, right? Just tell me the derivatives of each of these problems. I'm going to star this one because that's a beautiful drawing that we have here. And I'm going to star, I think that's actually, you know, most of them are right. So I'm just going to show this one right here. Take a look at this answer right here. Let's take a look and see if this person is correct. The derivative of x cubed is 3x squared. The derivative of x to the 4th is 4x cubed. Now here we go with these ones. Have you forgotten these special ones or not? The derivative of tangent is secant squared x, right? The derivative of cotangent, you're missing one little thing for your derivative of cotangent. Does anybody know what's missing from that cotangent? The negative sign. Yeah, the negative sign. Other than that, though, that's pretty much perfect. So that's the only one thing that is missing there. Let me see here. Let's go with, but I got sucked in by this beautiful butterfly that was drawn here. All right, let me see here. Here are these answers right here. I'm going to go ahead and hijack these answers right here. That looks good. I'm going to go ahead and take your answers. Thank you very much. So why did I have you guys and gals, why did I have everybody calculate derivatives again when we're doing these things for integrals? And I hope everyone can notice that if you know that when you're doing an integral, it's just the antiderivative, it makes it a little bit easier if you know all of your derivatives. Now, it's been a while though, right? It's been a while since we've looked at all of our derivatives. But let me go ahead and just double check with you here and make sure you understand. When you're doing your homework and whatnot, and they ask you to evaluate these integrals and you're asked to find antiderivatives, I'm hoping that you can see that the power rule also works backwards, right? So if I do the integral of like x to the 3rd, like we earlier, let's say we did earlier here, we did the integral of x to the 2nd, right? We saw that the integral of x to the 2nd, right? We saw that that turns into x to the 3rd, but then we have this guy right here, 1/3, right? And we did it for x as well. X by itself became x to the 2nd, but then we had 1/2, right? So the way we counteract this, right? And that's because right here, if you take the derivative of x to the 3rd, we end up with 3x squared, right? That x squared is the part that lines up with this, but we don't want that 3 there, right? So we cancel that out with these coefficients right here, right? So it works for really high degrees as well. If I had x to the 4th and I did the integral of this guy, this would be x to the 5th, right? But then to counteract that 5 right there, I just need to make sure I divide by 5, right? Hopefully, does that make sense when I'm doing this? This is called the power rule for integrals. It's like the power rule for derivatives, right? So let me show you what I mean. The power rule for derivatives is this. I say derivatives, funny. Derivatives, right? Power rule for derivatives is this idea. If I have x to the n, right, the derivative of this with respect to x, right, would turn into n times x to the n minus 1, right? So I would take that power, bring it down, and then I would take that power and subtract it from 1. This power rule also applies for integrals, but it just goes backwards. It just goes backwards. The power rule for integrals, right? If I had the integral of x to the n, right, dx, let's say, and I was doing this, this would become, right, x to the n. That's not an x, knock me, that's an n. X to the n plus 1, right? Because we talked about this, right? Integrals, derivatives are inverses of each other, right? So if a derivative will decrease your power by 1, the antiderivative will increase the power by 1. So that's what happens here, right? This was a power of 1, it became a power of 2. This was a power of 2, it became a power of 3. This is a power of 4, this became a power of 5, right? So hopefully you caught on to that if you were doing the homework, and if not, you'll catch on to it now, and you'll see that when you do these integrals and it's just a power by itself, you just convert it, you just add a 1 to that power, and then we divide by whatever that new power is. Whatever that new power is. And that's what that symbol is right here. This 1 over n plus 1 is telling us to divide by whatever that new power is. And this works if there's already a coefficient there. This is kind of neat. It's kind of neat. Check this out. If I have here the integral of 4x to the second, let's just say I have 4x to the, what's a good one? Yeah, why not? Let's go 4x to the second power, dx, right? And I was asked to evaluate this. The 4 just comes along for the ride, right? If you remember the rules or the properties of integrals that I had on there, I can bring out the 4 in front and I can just say, what is the integral of x squared dx? Well, the integral of x squared dx is going to give me x to the third times 1 over 3. Do you see the pattern here? Right? This 3 right here is the 2 plus 1, right? It's the 2 plus 1, which is following that n plus 1 idea. And then the bottom right there is also the 2 plus 1, which is giving me that 3. So that right there is the integral of just x squared. Don't forget, though, this in front of it, this number, this coefficient that's in front of it, is simply multiplying with this. So the 4 would just come along and multiply with this answer. And check this out. This would become 4 over 3 times x to the third. And whenever you do integrals, you can always double check it just by taking the derivative. Is this the correct answer? Well, take the derivative of it and see. When I take the derivative of 4 over 3 x to the third, 4/3 is your coefficient. What's the derivative of x to the third? It's 3x squared. What's going to happen to the 3's there? The 3's cancel out. I'm left with 4x squared. That matches with what the original problem was. And that's the beauty of these antiderivatives. You can always check it just by taking the derivative and, getting back to the original problem that you started with. So this is what the power rule. And the power rule doesn't, the n, by the way, it doesn't even have to be a whole number. This works if you do integrals with rational powers as well. So if I had something like the square root of x, right, dx, and I asked to do this integral, I would just rewrite this as the integral of x to the 1/2 dx. So when I do this, I just apply the power rule again. This is going to be x to the 1/2 plus 1. This is going to become 3 over 2. Now, I know what you're going to think right now. Man, I hate fractions. I don't know why students think that, but maybe I'm overgeneralizing. Maybe you guys don't hate fractions as much. Maybe you guys are better at fractions now than my past students, but I like these. These are actually not too bad. This right here is telling me to do 1 over 3 over 2, which if you think about it, when you have a fraction over a fraction, that you just keep it and you flip it right side up. So instead of 1 over 3 over 2, you could have just written this as 2 over 3. That way it'll cancel out and you'll have a coefficient of just 1 right there. Have I lost anybody? Are you guys doing all right? Are you guys able to follow along? I'm throwing a lot at you right now, but it's nothing too crazy, I'm hoping, right? It's just something that I'm hoping you realize when you start doing a lot of these integrals or you're doing a lot of these antiderivatives. If it's just like x to a power, it's just the power plus 1, and then divide by that new power. And then again, check it. Take the derivative of what you just got. Do you end up back at where you started? You should all know how to take derivatives of these functions and see what you get. With that being said, there are some problems that they ask you to do the integrals, and they're going to be a little bit messy. And when they are a little bit messy, it is going to ask you to think outside the box a little bit. So, for example, let me show you what I mean. For example, right here. Earlier today, you told me that the derivative of cotangent x was negative cosecant squared x. And that's perfectly fine. But now that you know this, you ready? You are going to get some problems where they ask you to do the integral. Whoops, fat fingered something. Hold on. Hello, mouse. There you are. There we go. Okay, so you are going to be asked to do the integral from 0 to pi over 2, for example, of cosecant squared x dx. And if you don't know what derivative leads you to cosecant squared x dx, then you're not going to be able to do this problem. If I was given this problem and I was asked to evaluate this and I didn't have the calculator section, I would look at it and just say, I don't know this one, because you can't actually, I mean, you can do it, but it's just not worth the effort. It's easier. This problem is easier if you know that this is the derivative of cotangent. So if I was evaluating this integral, to find the antiderivative of cosecant squared, I need to just know what the derivative of cotangent is. All right, so this right here, if I were to evaluate this, this would be negative cotangent of x evaluated from 0 to pi over 2. And this is where things get a little difficult for some students. Most calc students are very, very good with the power rule, but what separates the 4s from the 5s, this is, by the way, this would not make it so that you fail the AP exam. This is just something that separates someone from getting a 4 to getting a 5, is knowing all of their trig functions and all of the trig derivatives. And if you know all the trig derivatives, you know all the trig, well, you know most of the trig antiderivatives. So for example, if I was to ask, hey, what's the integral from 0 to pi of secant x tangent x dx, you need to know that this is going to be equal to secant x evaluated from 0 to pi. How do I know that? I double check this by taking the derivative of secant x. What's the derivative of secant x? Anybody have a guess? What's the derivative of secant x? If you were a guessing person, secant x, tangent x. It's exactly what I have there, you know? So this is a time that you might want to go back and start practicing, not even practicing. If you guys want, I can give you a cheat sheet on this. I'll show you what the cheat sheet is. You ready for this? You just go to Google and you type out list of derivatives. And there's a bunch of sites that have different ones that you can use. Oh God, that is, just, why are you, why is your, hold up, there's got to be a better one. Are you good? I mean, a little bit better, a little bit, but you know what I mean though, right? See here, derivative of sine is cosine, derivative of secant is secant tangent. They use the letter u and they put it in with the chain rule. You can just replace them with x's if you want, but that's the idea here. And please don't forget the inverse trig functions. They're going to be in there as well. But for integrals, I'm just letting you know right now. For integrals, for derivatives, you want to know all 6 of them. But for integrals, most of the times, they're just going to be in the form of either arcsine or arctangent. There'll be one form or shape of that. What about the problem like 1 minus the square root of x over the square root of x? 1 minus the square root of x over the square root of x? Or 1 minus the square root of x all over the square root of x? The second one? That one. We will eventually tackle problems like this, but not in this chapter. Did you get one in this chapter that was like this? Actually, no, that's a lie. We can tackle this problem. We need to do some algebra. Actually, that's a good point. So before let's put this one. Yeah, let's put this one on hold. Let's put this one on hold. Actually, not on hold. Let's keep this one. I'm going to show you how to do problems like this actually right now. That's actually, thank you. I actually forgot about this. So let's talk about this problem. So right now we know, just the basic derivatives and what they link to. I'm telling you right now though, for this chapter, we're not going to be doing things like chain rule or product rule or quotient rule just yet. In fact, I don't think we do product rule until BC. But here's the deal. How would I attack a problem like this? If I was asked to find the integral of this dx, I can't do it this way because it's not an easy one to find the antiderivative of, right? So let's take this one down. How would I attack this problem? And the way I would attack this problem is try to rewrite it into a form that makes it easier to deal with. This is not an easy form to deal with. Easy form to deal with would be x to the n, right? If I had the integral of x to the n, I know that the antiderivative of this is going to be x to the n plus 1 over times 1 over n plus 1. Well, This isn't of the power form, but I can actually rewrite it. You ready? Follow along here. I can rewrite this integral of this fraction, right? I have, if you know about fractions, I can split this up into two separate fractions. I can write this as 1 over the square root of x minus the square root of x over the square root of x. Are you okay with that? Oh, I'm sorry. dx. Does that make sense? Are you guys paying attention? I'm splitting up my fractions. If I had something that was like x plus 3 over 5, all I'm doing is rewriting it as x over 5 plus 3 over 5. And you're allowed to do this, by the way. It's just that when you're learning math, they always tell you to compress everything into one thing. But in calculus, sometimes it makes the problem easier if you can split them up into individual terms. From here, I'm going to simplify this into a power form. 1 over the square root of x is the same thing as x to the negative 1/2. Right? How is that? Well, 1 over the square root of x is the same thing as 1 over x to the 1/2. Right? Which is the same thing as x to the negative 1/2. So that's how I did that one right there. Minus the square root of x over the square root of x. All right, that's just 1, everybody. Square root of x over the square root of x, that's just 1. It's the same stuff over the same stuff. Simplifies out to 1. Now that I have rewritten it, would you agree that we can actually find the antiderivative of this a little bit easier, right? The antiderivative of this is going to be a little bit easier, right? Because I can use the power rule here now, right? The power rule here is going to tell me that this is going to become x to the, right? The integral of x to the negative 1/2 dx is the same thing as x to the negative 1/2 plus 1 times 1 over negative 1/2 plus 1. That means that this is going to be equal to negative 1/2 plus 1 is the same thing as positive 1/2. This right here is going to simplify out to 2. So this right here is going to the integral of x to the negative 1/2. The antiderivative of that, I should say, is 2x minus the antiderivative of 1. What's the function that when I take the derivative of it, I get 1? Why, that's just x. Evaluate it from whatever a to b is. Which, by the way, this would simplify to just x. Is that okay? Have I lost anyone? Does that make sense as to what I did? Hopefully it does. Hopefully you can see it, right? When I did this integral over here, I did it by itself over here, and all I did was just use the power rule that we've been doing. And it's okay that the power is not perfect, but the hard part is getting to that power rule. And to get that, you need to see how good are your algebra skills right now. Some problems are easy to convert like this. You can convert it using your basic algebra skills to split them up into individual terms and then just do these ones by rewriting them out. Some of them, oh, do you have this written down? Can I move forward, or are you guys still copying it? I'm gonna give you a minute to copy it. Even if you're done, just give everybody a minute to copy this, let it process. There is some cases where your algebra skills will not come into save you. And this is where we actually have to think outside the box and start thinking about, well, what's the derivative of it, and see if we can work our way there. Where'd the 1/2 go? Which 1/2 are we looking at? 1/2 on the left, 1/2 on the right side? Okay, 1/2 on the right side. This right here, is this one the one you're asking about? Or is it, oh, good catch, Brian. That 1/2 did not disappear. I forgot to write it down over there. Thank you. I was just checking to see if you were paying attention, and Brian, you were paying attention. That's right. I don't make mistakes, right? I was just seeing if you were, seeing if Brian was the only one paying attention. Good job, Brian. It wasn't that I made a mistake or anything. That was clearly on purpose. Clearly on purpose. Sure. I know, Brian, right? Yeah. Sure. Indeed, sure. Yes. I promise you, I kind of know what I'm doing. Sometimes. We all need spring break, don't we? All right. I'm scared now. Don't be, Calvin, don't be. We all, we're all doing fine. We're all doing fine. We all got this. Don't worry about it. All right. Here's one problem I wanted to share with you, right? That's a little... That's the word I'm going to use. Let's say I have here the integral from 0 to 5 of 7 to the x power dx. Yeah, 3 to the x, close enough. I'm going with a 7 because I like 7s, but same type of problem, Monica. Now, this one, power rule does not apply. Power rule applies to the integral of x to the n, right? And n is your coefficient usually. Not the other way around. This is n to the x. This is an exponential. This is an exponential. So in order for me to do this one, right, I can't use the power rule. I have to know about my exponentials, which means I need to figure out, do I know what's the derivative of 7? What's something that would give me if I took the derivative of 7 to the x? Do you guys remember? What is the derivative of an exponential? Right? If I didn't have 7, what if it was just a to the x? Do you guys know what the derivative of a to the x is? E to the x would work. Wait, is it e to the x times 7? Oh, it's e to the x times 7. Hey, you know what we just found? A list of derivatives. Let's go look at our list of derivatives. Is there an exponential in here? Do you see the exponential? The derivative of a to the u is a to the u times ln of a. It's right here. I can't highlight it. But let me show you what that means. So the derivative of a to the x is the same thing as a to the x times ln of a, right? So that means the derivative of 7 to the x is equal to 7 to the x times ln of 7. This right here, this one right here, definitely matches the derivative of this one. So the original function should be, 7 to the x, right? The original function should be 7 to the x. But there's some stuff with it that we need to cancel out. What do we need to cancel out if I were to take the derivative of 7 to the x? So it's not just going to be 7 to the x. It's 7 to the x times 1 over ln of 7. I need that ln of 7 to cancel out. So if I put in here 1 over the ln of 7, if I were to take the derivative of this, the derivative of this would give me this whole thing, right? Excuse me. So check this out. If I do this right here and I take the derivative of this whole entire thing, I will get this because the derivative of 7 to the x will give me 7 to the x times ln of 7, which is going to cancel out with 1 over ln of 7. So this right here is the antiderivative of that. And we'll talk more about that. But again, the idea of this is you need to be able to look at a problem and try to guess, what do you think the antiderivative is going to be? This one, there's no tricks or gimmicks or other than just you need to know that the derivative of an exponential is itself multiplied by ln of itself. Right? This is not the same if I was doing 0 to 5 of e to the x dx. This one's actually easier because the derivative of e to the x is just e to the x with no other number. So the derivative of 1 over ln of 7 is 1 over ln of 7. No, the derivative of 1 over ln of 7 would just be 0 because, well, this is a constant. But that's the constant that we need to put in front there so that it'll cancel out with this ln of 7 when I take the derivative of this right here. If that makes sense, Brian. Yeah, it's a little strange. Exponentials are a little weird ones. They're a little strange, a little weird. But for e to the x, if my base was e on our exponential, the ln's would cancel out anyways, right? It's supposed to be e to the x 1 over ln of e, but 1 over ln of e, that's just 1, because ln of e is just 1. And it just cancels out anyway. So if we could just say the antiderivative of e to the x is just e to the x, evaluated from 0 to 5. Okay? I'm not going to give you an exponential on your test. I'm just letting you know that right now. I'm not going to tell you, hey, what's the integral of 3 to the x dx on this chapter. Maybe in the future chapters, but not this chapter. But even if I did, I think you can get it now. I think you can get it now. All right. Hopefully with that, you guys will be able to do all the homework problems now. I put 2 of them up a little late, sadly. So, you know, get into there and do those whenever you can. They are practice problems for the fundamental theorem of calculus and the mean value theorem using integrals. Okay. All right. That's that one right there. Let's go ahead and get on to today's, I think, this unit's last lesson. So let's go ahead and do that today. The last lesson. The last lesson is the trapezoidal rule. Trapezoidal rule. You guys remember RRAM, MRAM, LRAM? This was in the AP videos? Good, 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 good. So hopefully it's not new. So, AP Calculus, for some reason, loves doing these approximations, even though integrals will get you the exact value every single time. If you know what the function is, they'll still give you problems where you need to know how to approximate it. So what I'm saying is this, right? If I had a function and I didn't know what the function was, I just knew what it looked like. Let's say I knew it looked something like this, right? And I had a set number of rectangles, right? RRAM was this idea that if I was going to go from A to B, right, that I would make rectangles from the right side of my function. So this is the right side right here. This is the right side right here. Right? This is the right side right here. Right side right here. Right side right here. Right? So that's what RRAM would do. RRAM would use rectangles, and we would calculate the height of our rectangle, right? The height of our rectangle was always f of whatever x sub k value was, right? And then the base would be the delta x's, right? And when we did RRAM, most of the times our delta x's were always equal all the way across, but sometimes they weren't, and we found out it was close enough. And then the heights would be based off of the function evaluated either on the right hand of the rectangle, the left side of the rectangle, or the midpoint of the rectangle, right? You have those 3 points right there. So if this is the last rectangle, RRAM uses this one, MRAM uses this one, and LRAM uses this one, right? So each of those are the different methods that we learned, right? And I kind of left it at that, and I was like, I was always in a hurry to, like, I was too excited. I wanted to get you into the integrals because, you know, that's the calculus part of it. This is like geometry, you're just adding up areas. Calculus part of it, you're still adding up areas, but you're adding up infinitely many areas. And I got a little too excited and I went too far into that. The trapezoidal rule is the 4th rule, and it's the most I've seen in the past 3 years, the most question on the AP exam that I've seen out of the 4 rules that are there. Right hand rule, R rule, L rule, RRAM, MRAM, and LRAM are the basics of these approximation ones, and I think they're like the most important ones. But trapezoidal rule has been lately the one that has been showing up the most on these AP exams. And with the trapezoidal rule, it's not much more difficult, I would say. It's just much more annoying, I would say. So for the trapezoidal rule, right? I always like mess up the spelling on trapezoidal. The trapezoidal rule, right, is it doesn't make rectangles. So if I'm going from A to B right here, right, and I have a bunch of these rectangles that are in between, just like the other ones, or a bunch of like delta x's here, here, and here, right, I don't actually make a rectangle. At each of these points, I go up to it exactly where this point is, and I go up to exactly where this point is. So I use both the left hand and the right hand, and then I just connect those 2 dots together. So instead of drawing out a rectangle, I make a trapezoid that's standing straight up. So the trapezoid looks like this, actually. If I took it and I rotated it, it looks something like that. You see it? There's the trapezoid right there. Now, do you guys know how to calculate the area of a trapezoid? Do you know the formula for the area of a trapezoid? If you watch the video, they should have specified it, but if not, it's okay if you don't. The area of a trapezoid is going to be 1/2 base 1 plus base 2 times the height. I think when you first learn it, they show it to you like this. B1 plus B2 divided by 2 times the height. It's the same thing. It's the same thing. It's the averages of the bases times the height. Now, this is the part that's going to be hard for some people to see. Base 1, base 2, right? Or it could be the other way around if you want it. We can make that base 1, that base 2. It doesn't really matter. The bases are the lines that are parallel to each other. The height is the perpendicular distance between the two, right? It's not that slant distance. It's the perpendicular one. So this right here would be the height. If you look at it closely right here, if you rotate it back, that means that your height is the same thing as what your delta x's are, your dx. I'm going to write it as a delta x, right? The difference from one x value to the next. Okay? The heights, I don't know if you can see this or not, but the height of base 1 is the same thing as f of x, right, of the right side of your rectangle. The other base is the function evaluated at the x value that's on the left side of that rectangle. So once you get those values to calculate the area of this trapezoid, you just plug it into this formula. You do this base plus this base divided by 2 multiplied by the height. And that's going to give you the area of this said trapezoid. And trapezoids have way less errors than right-handed rule or left-handed rule. It might be the same for the midpoint rule, but it all depends on how much curve there is on the function that you're dealing with. So that's the trapezoid rule in a nutshell. How do we do the trapezoid rule? Well, let's take a look. How do we apply the trapezoid rule? All right, so let's take a look here. So let's say the reason why most of these problems show up on the exam is because you're not given the function, so you can't just evaluate it using the antiderivative, right? We understand, though, that if you're given an integral, it's the area underneath the curve. And if you have a function, we just take the antiderivative of that function and evaluate it. Not the case if they only give you this as your function. You ready? They tell you that y is a function that's continuous that is evaluated at these points right here, and they give you a table. So they give you an xy table. So for the x values, we have 0, 1, 2, 3, and 4. And the y values, we have 5, 7, 4, 6, and 5. Right? And they want us to find the area, right? They want us to find the, you know what? Hold up. Let's not call that y. Let's call that f of x just to make it simple. And what they want us to find is they want us to find the integral from 0 to 4 of f of x dx. And what I'm saying is this, right? If we knew what f of x was, we would just say like, oh, that's easy. That's equal to the antiderivative of x evaluated from 0 to 4. I don't know what the function is. I can't find the antiderivative of it, so we can't do it this way. This does not work for this problem because they don't give us the function. They just give us a table. They give us a table. So for this one, we're going to need to approximate this, and I'm going to say I'm going to approximate using the trapezoidal rule. Oh my God, knock me. Can you like trap no, trap E? E, knock me. Trap E. Oh my goodness, that's a Q. Trapezoidal rule. Whenever I do the trapezoidal rule, I like to draw it out, but it's actually frowned upon because sometimes numbers come out negative and your drawing gets all kind of warped, and I'll show you what I mean. But for right now, this one is all positive. Let me show you what this looks like. So since we can't do it this way, right, I'm going to draw this out. So what does this look like? Well, at x equals 0, the f of x value or the y value is equal to 5. So this goes up here to 5. Right? So that's about, right, 1, 2, 3, 4, 5. That's about right there. Right? So that's that first dot. The second one is at 1, 2, this goes out to 3, 4, right? So at x equals to 1, it goes up to 7. That one goes up to here, right? At 2, it goes up to 4, which is right here. At 3, it goes up to 6, which is right there. And at 4, it goes up to 5, which is right there. So the function, I don't know what it looks like. It could look something like this, right? It could look something like this, right? I don't know what the function looks like, but I can estimate the area given the points that I have. Now you ready for this? What I'm going to do is draw trapezoids here. How many trapezoids do you think I can draw from 0 to 4 with the points that I'm given here? Anyone have any guesses? Any takers? 4. Monica's saying 4. There's one that I can draw. Right? Here's another one that I can draw. Here's another one I can draw. And here's one more I can draw. So to get the area underneath this curve, I'm just going to calculate these trapezoids and add them all up. You ready? So for the blue one right here, to get this area, right, that area is going to equal to, remember, if you don't have this formula down, right, the area of a trapezoid is equal to 1/2 base 1 plus base 2 times the height. So here we go. For this blue one, it's going to be 1/2. What's base 1 equal to? Base 1 is this height right here on the left-hand side, and that height is 5. How do I know that height is 5? Right here. They tell us that it's 5. See that? Plus base 2. Base 2 is this one right here. What's that height? That's right here, isn't it? That's the height. I'm sorry, that's a base 2 of 7. And what's the height? The height is the delta x. How much is it changing from the left hand to the right hand? How much is it changing to go from 0 to 1? What's that h? What's the jump from here to here? The jump from here to here is 1. So the height for that is going to be equal to 1. That's right, Monica. That's right. Very good. So we go ahead and evaluate this and calculate it, right? And do that. I'm going to do that later. Do the same thing for the red area, right? For this red area right here. That's going to equal to 1/2. You ready? The height on the left-hand side is this one, right? It's 7, plus the area on the height of the right base is going to be 4. Are you guys doing okay? Are you guys following along? How did I get the 7? The 7's this one right here, right? So let me put that out right there. The 7 is shared between the blue and the red, right? Whereas this one right here, this 5 is just by itself. Right? This 4 is going to be this height right there. And then the difference from here to here is this delta x. That's also equal to 1. Right? To jump from one to the next, that's also 1 right there. We're going to keep going. We're going to keep going. Next one up, purple here. Right? We're going to do this area. This has a height of 4 as well. Right? So let's go ahead and do that. Or a base 1, I should say. So this is 1/2. 4 plus this one over here, which is clearly a 6, because again, it's this part up here, right? How much does it go to jump from 1 to the next? It jumps by 1, right? So this is 4 plus 6 times 1. That goes over there. And we're going to finish this off with this last one right here. This 6 is shared by the purple and the green, so this is going to be the area of 1/2 of 6 plus this height right here, which is 5, times 1. Ta-da! And once you add all this up, this gives you the area underneath the curve, which is an estimate for the integral of this function. So once you do that calculation, you get your answer. I'm not going to do the calculation. It's just calculator work at that point, or just, calculation work at that point. But I do want you to take a look at something really neat here, is that when you do the trapezoidal rule and the bases are all equally distanced from each other, there's something neat that kind of happens here. It doesn't always happen, but it happens on the ones that have equal delta x's all along the way. If they have equal delta x's all along the way, you don't have to do this, by the way, but if if you're interested in this stuff, some people like to write it out like this. If you were adding this all up, right? This is the idea. You're supposed to add these all up. And we can just stop here. You don't want to, if you don't want to write this part down, you don't have to. But some people love seeing patterns. And when I say love, I mean love seeing patterns. Some people who notice this, they notice that if you're doing this, right, it's supposed to be the blue one, right, which is 1/2 of 5 plus 7 times 1, plus the red one, which is going to be 1/2 of 7 plus 4 times 1, plus the next one, right, and so on and so forth. And what some people notice is that if all the delta x's are the same, there's a really neat little pattern that goes on here. The 1/2 is also the same for all of them because of the area of the trapezoid. They'll write the 1/2 in front, and inside, they will just write down all the numbers that need to get added up and then multiply by the delta x's at the end because there's a bunch of delta x's at the end here. So inside, what do we have? We have a 5 plus, how many 7s do we have adding up together? There's 2 of them. How many 4s do we have adding up together? There's 2 of them. How many 6s do we have adding up together? There's 2 of them. And the last one is a plus 5 at the end. That plus 5 at the end is not the same as the plus 5 up front, right? And this is multiplying by 1. So what I'm saying is this. If you have all of these values, you can write a formula that will calculate the trapezoidal rule for you if all your delta x's are the same. This area is just going to be equal to 1/2. You ready for this? This 5 is technically the first term, right? It's actually f of x sub 0 plus 2 times f of x sub 1 plus 2 times f of x sub 2 plus 2 times f of x sub 3 plus the last one, f of x sub 4. All of this, of course, is being multiplied by the delta x's of each one. And I know that looks kind of funky and kind of crazy, but it's just the idea that every term that's in the middle here is added up twice. The last ones are added up just once. Once you add them all together, you divide it by 2, multiply by the delta x, and you'll get your area. And like I said, there are some calculator apps, if you guys want to look into it, you could plug in these values for x and f of x, and it'll give you the trapezoidal rule for you. The only problem is if you look this up, it's a great tool to have, and it will calculate it right for you, but it will only calculate it right for you if each delta x are the same. This one, I don't know if you understand what I'm saying. The delta x's here are all the same because it goes from 0 to 1, then it goes from 1 to 2, and then it goes from 2 to 3, and then it goes from 3 to 4. Each of these delta x's all equal to 1. That's most of the cases, but not all of the cases. Sometimes your delta x's will be different. But let me show you. By the way, did anyone do this calculation? Did anyone add these all up? Does anyone have the answer? I don't have the answer for this. Monica, you did it? So this area right here, if you do this calculation, you add it all up, you get 22. Monica, I'm trusting you on this one. So I think you're right. I have no way of, I'm not actually going to plug that in and do it. So I think you're right, though. I think Monica's right. We'll go with that one. It is 22. But this equation thing here, you don't have to write that down. I just wanted to show you because it is a pattern that shows up, and being mathematicians, you love looking at patterns, right? You love noticing patterns. You just don't know that you love noticing patterns. All right, let me go with one more problem before we call it a day here, and I want to show you one more example here. And don't worry if you're not comfortable with this, we'll keep practicing this next week before we start reviewing for your test. All right, so let's take a look here. Selected values of f of x are shown in the table below. What is the trapezoidal sum approximation for the integral from 1 to 11 of f of x dx using 5 subintervals as indicated by the table? 5 subintervals means that we're going to be having 5 trapezoids. 5 trapezoids, right? So again, you can draw this out, but now that we know that we're using trapezoids, right, we can just figure out the area of each of the trapezoids, right? So let's go ahead and do that real quick. So the integral from 1 to 11 of f of x dx is going to equal to, and we're just going to do these one trapezoids at a time. So my first trapezoid is going to be right here. This is going to be my first trapezoid. And if you need to draw it out, you can, right? So it's going to be from 1, it goes up to 12, right? And then the next one is going to be 4, and 4 goes up to 4. So that first trapezoid is right here. It goes up to 12, comes down to 4 right here, and we need to figure out our delta x right there, right? So that's the trapezoid right there. This is 12, this is 4, right? So how to calculate that area? That area is going to be 1/2. First base is 12 plus 4 times the delta x, and the delta x is how much does it go from here to here? And what is that delta x? How much does it go from 1 to 4? I hope you guys can all see that. The delta x is 3. Delta x is 3. How's everybody doing? Haven't lost you yet, right? We go to the next trapezoid. Next trapezoid is going to be from here to here. And let's draw that out. The first one is 4 and 4, so we already have that. And then it goes to 5, right? So I should put these values down here. This is 1, this is 4. The next one's going to be 5. 5 is pretty close, so I'll put it right there, right? And at 5, it goes up to 3, it looks like. It looks like it goes up to 3, so it's going to curve down like that, right? So how do I calculate this area of this trapezoid? Well, this one's going to be 1/2 4 plus 3 times the delta x that goes from here to here, and that delta x that goes from there to there is 1. And we just keep doing this until we have all 5 trapezoids, right? Until we have all 5 trapezoids. So next one up will be this one right here from here to here. This is going to be plus 1/2, right? I'm not going to draw this one out. I'm just going to write it out. This is going to be 3 plus 2 times the delta x from here to here, and that delta x is 1. We just keep going. Next one up, this one right here. I'm only at 4 intervals right now. Once I get to here, there's going to be 1/2, 2 plus 1 times this delta x from here to here. That delta x is 2. This delta x is 2. So count it out, guys. Count it out. 1 interval, 2 interval, 3 intervals, 4 intervals, right? They give us just enough to do 5 intervals, right? Or 5 trapezoids. So we're going to go ahead and get this one right here. This is the last one from here to here. This is going to be plus 1/2. What's that first height? That's 1 plus the second height, which is 2, times this delta x. What's delta x from 8 to 11? 8 to 11, that's going to be a delta x of 3 right there. And that's it. So to estimate this integral, right, it's going to be equal to, do this integral right here. I think this is going to be, man, my math is not as good as it used to be. Here, this is going to be 16 divided by 2 is 8. 8 times 3 is 24 plus 7 over 2, what is that, 3.5 or 7 over 2, however you want to write that out. This is going to be 5 over 2, which is 2.5. Over here, we're going to have, that's going to be a 3, I believe. And then this one last over here is going to be a 9 over 2, which is 3.5. So my answer for this, the integral from 1 to 11 of f of x dx, right, without finding the antiderivative, and just finding the area of a trapezoid and adding them all up together is approximately, I don't actually know the exact value, it's approximately 37.5. 37.5. How do you feel? I probably should have showed you this when I first showed you approximations, but I felt like you guys, no, it's not, I shouldn't be blaming you guys. I should have showed you this when we first did LRAM, RRAM, and MRAM, but like I said, I got a little too excited. Once we get to integrals, I just could not wait to show you guys integrals and antiderivatives. Trapezoid rule falls under the LRAM, RRAM, and MRAM topics. It's just a tool to help you approximate the area underneath the curve if you don't have the function. Oh, did I mess up? Is it 36.5? Ava? Did I mess up there? Is not 37.5? Whoops, wait a second. Oh, that's my fault, actually. That's this one right here. I messed up on this one. 1 plus 2 is 3. 3 times 3 is 9. 9 over 2 is not 3.5. Knock me. 9 over 2 is 4.5. And now it should be 37.5. And Ava, good job on catching that. See? On purpose, just to see if you're paying attention. And Ava, good job on paying attention and seeing that there was a mistake there. But yeah, good job. All right. for the trapezoidal homework. I should have that up by the end of today, hopefully. If not, someone send me a message so I don't forget. I've been bad at putting up your homework on time, so I apologize on that. But that's the reason why those 2 assignments got put up at the same time on your Canvas page. I feel a little guilty, but I think you guys can work those problems out, no problem. But yeah, so that's it with this section. That's it with this chapter. Trapezoid rule was the last one. We could do some more practice stuff, but I'm going to put the homework up first for you guys to try it out. And then next week, like I said, next week, we're going to start reviewing. I think we're going to review on Monday. Would it be too quick if I just gave you guys the test before spring break? That'd be too much, wouldn't it? What sucks is Thursday is a minimum day, so we don't get the full day, and Friday we have no school. So I really would have liked to have given you the test next week before spring break, but I don't think that's going to happen. What about a take-home test? How would you feel about a take-home test? Do it over spring break. That'd be an interesting one. I don't know. I'll send out a survey. Like I said, there's a couple of questions I need to ask you guys and gals. But I think that's it for today, at least. So again, I apologize for putting these homeworks like up back to back like this. One should have been up on Monday. The other one should have been up yesterday on Tuesday. Check your Pear Deck slide. Slide 4. Let me see. Oh my God. All right, we're gonna call it there, but before we call it, let's take a look at this one. Beautiful drawing. A good one to wrap up on. Calvin, is this what you do during my class while I lecture? Or is it because you already know the trapezoidal rule so well that you're just like, I'm just gonna spend this time drawing? Evidence is all there. All right, everybody, I'm gonna wrap it up here. This is the last one of the like I said, the topic of this unit. We've covered everything from LRAM, RRAM, and MRAM, along with Riemann sums, which was the idea of using those MRAMs or RRAMs going all the way up to infinitely many rectangles, and then actually calculating some integrals using the calculator and then using the antiderivatives to do it. We'll practice more. I'll get the study guide for you guys out after this homework assignment. I'll put it up sometime over the weekend. We'll go over it next week on Monday, and then Tuesday of next week, I think we're just going to do a big review session. I wanted to give you the test, but that's going to be too much. So we'll just do a big review session. And then, oh God, what are we going to do on minimum day? Knock me on Thursday. We'll figure that out. But anyways, I'm going to wrap it up here. Let's call it a day. And I'll say this right now. Just have a good weekend, right? Stay out of trouble. Stay out of jail. Don't get pregnant. All right, if you have questions, I'll be in my office hours today from 1 to 2. And yeah, stop by if you have any questions. All right. Bye, everybody. Have a